Okay, so we've talked about magnetic forces on current carrying wires. If you watch the Dan Fullerton videos, you already know what I'm about to talk about and you can ignore it. But let's say we have a current carrying wire within an external magnetic field. So here's our magnetic field lines. Let's say a uniform magnetic field. We can generalize this to talk about the equation that describes the total electric field on this current carrying wire. Okay. If you didn't watch the Dan Fullerton videos, you probably won't pay attention. So we know that there's a bunch of electrons moving through this wire. Technically, they're moving this way, but we're going to consider positive charges moving in the direction of the current. And so I'm going to choose the charge that's right here. I'm going to call that Q. Okay. That charge, that positive charge, is flowing this way with a drift velocity. Right. Drift velocity is the velocity that you would measure the proton actually flowing through the wire with. And so I'm going to draw that velocity vector here. That's going to be the drift velocity of that electron. And I'm going to talk about, because everything's changing here, right? The magnetic force on every charge in this wire is going to be different. And so I got to talk about the charge actually dq, not just q. You talk about charge dq, traveling with some velocity here, as that charge, I'll just call it charge, as that charge moves through an infinitesimally small displacement, okay? We used to call that dr, right? When we're talking about charges going through, say, a potential difference, we'd integrate E dot dr. But since we have a wire here, the convention is that we call it dl, okay? Where L stands for an infinitesimally small length of wire, or length over which the charge will actually move. And so dq here is going to move, use a green, through a displacement dl. And again, I call it dl because it's a length of a wire segment, an infinitesimally small length of a wire segment. Notice that the angle between the drift velocity and...
Scalar?
What's that?
Is it scalar? Like L for a scalar? Maybe?
No, it's a vector.
Okay.
It's a vector. Yeah, dl is going to be a vector, and it's just the length of wire through which the charge is moving, and the vector points in the direction that the charge is moving.
Okay, so it's basically same thing as R.
Yeah, it's the same thing as dl.
Okay.
Yeah. And we know there's an angle theta between the drift velocity and the magnetic field. Hence Q times the cross product of V and B. Okay. All right, well, let's talk about the magnetic force on this charge dq. In general, if we had a situation where nothing was changing, we know the magnetic force is just Q times the cross product of V and B. But here, we don't. We have an infinite number of different magnetic forces on each of the infinitesimally small charges moving through that wire. And so I could say the magnetic force on this charge, dq, would be the differential magnetic force. Sorry, that's a vector. Is going to equal charge dq times that drift velocity crossed with the magnetic field. Right? And then I can set up an integral and calculate the total force on the entire wire. Okay, if I do it this way. And we also want to note that current is defined as the rate at which charge flows, dq dt. Hence, dq equals I dt. Right, just multiply both sides by dt. Again, Dan Fullerton goes over this, but I think it's important to go over it also. So I'm going to replace dq with current times dt, because we don't want to express our magnetic field, magnetic force, in terms of every single little charge dq that's going through that. We can summarize that with this amount of current that's not going to change, right? It's going to be the same number. So it simplifies the mathematics here. So it's I dt times drift velocity of the charges crossed with the magnetic field.
So why is it not an infinitesimally small velocity?
Because it's an infinitesimally small charge that's actually moving with some instantaneous velocity, right?
Okay.
So it's not like just because we're talking about a very small, infinitesimally small charge moving through an infinitesimally small displacement, it's still got some macroscopic velocity that it's moving.
Yeah, that makes sense.
Good question. All right, and so we also know that velocity is simply displacement over time. Well, our displacement of this charge dq is dl, which again is a vector if we're indicating the velocity vector in terms of it. So let's kind of bring that back, divided by time, right?
Wait a minute.
And so yeah, so when I do that, I have dFb, the differential magnetic force, equals the current times dt times dl dt crossed with b. And when you're dealing with cross products, the properties of cross products and stuff, just like derivatives and integrals, you can pull constants out. So I can pull this 1 over dt out, and it will end up canceling with this. And so I get the differential magnetic field is equal to the current times dl cross b. And then I can just integrate both sides to get the total magnetic force on this wire. This is a general expression, right? It doesn't matter if the wire is curved or something. We get that the total magnetic force on that wire is simply the integral of the current times dl cross b. And that's what's on the formula sheet. Okay. In this class, you won't deal with a situation like this because you need to take third semester calculus to get used to doing line integrals and that kind of an integral, where everything's changing, right? It's pretty complicated. For us, it's going to be like square loops of wire, right? So if you have a magnetic field, say, coming out of the board, you have a magnetic field coming out of the board, and you have a wire that looks like this. Right? This is going to be our basic electric motor. If I was to indicate the direction of the currents through this guy, it might be coming down here, be going over here, down here, over here, right? Notice that the angles are all going to be 90 degrees, right? The angle between the current and the magnetic field. So this simplifies, because dl cross b is going to be dl times b times the sine of the angle between them, which is just going to be 1. And dl is just going to end up being the length of each individual line segment, which I can do individually, right? And so this is what's on the formula sheet, but generally this ends up being something like the force, magnetic force on a straight line wire carrying current would just be in the proper configuration where the magnetic field is 90 degrees to the current. It's just going to be, so sometimes, it's going to be I times the length of wire, we can call L, times the magnetic field. Right? So it'll simplify to that. If the current and the magnetic field are perpendicular. If they're parallel, then the angle between them is just 0 and there's no magnetic force. So those are the simplifications that you'll have in this class when you have situations like this. Okay? And then when you learn vector calculus in college, you'll learn how to talk about this kind of a situation. But we won't see that in this class.
I'm not going to college this year.
For those of us that are going to college. Obviously, Mr. Nelson's not going to college.
So what kind of stuff would you calculations be useful in the real world? Like what kind of engineering would use this kind of stuff, like calculating?
A stupid thing.
Let me